We're going to pick up where we left off in our Chapter 5 notes. We already looked through an example with Twitter, so let's look at another one with football. It says we previously noted that between 1974 and 2011, there were 460 NFL football games decided in overtime, and 252 of them were won by the team that won the overtime coin toss. Is the result of 252 wins in the 460 games equivalent to random chance, or is it significantly high? Remember, we can answer that question by finding the probability of 252 wins or more in 460 games, assuming that the wins and losses are equally likely. So, if we think about what's going on here, we're assuming that wins and losses are equally likely. That means our P, our probability of success, which we'll call a win, was 0.5, and the probability of a loss, our failure, is exactly the same thing. Now we're looking at 460 NFL football games. That means our N equals 460. Our X is where it gets a little weird. We want that 252 wins or more, because remember that significantly high definition is that it's 0.05 is that value or higher. If it's less than our 0.05, it's significantly high. So that means our X is really all of the numbers 252 up to and including 460. So trying to use that binom PDF and calculate each one of them individually is going to be way too time consuming. Likewise, trying to use that list function and add them all up will likely be too time consuming and will likely make a copying error. So instead, we're going to use binom CDF. If you remember, binom CDF calculates the probability of that number and below. So whatever you enter for X and below. So if we're trying to picture what's going on, what we actually want to find is 252 up through 460. The issue is our binom CDF is going to calculate stuff including and below that number all the way down to 0. So we don't want our binom CDF to include our 252. So when we're plugging it in, we're going to count 251 through 0. What's the probability of that many wins? Then we can use our complement rule. So I'm going to use that binom CDF. To get there, we're going to go second distribution, which remember is on top of vars. Then I'm going to choose option B, which is our binom CDF. If you have the one that prompts you for things, you're going to put in that your number of trials, there we go, is 460. That's our N. The probability of success is 0.5, our winning those games. And then our X value is going to be 251. If you don't have the one that prompts you, you'll still choose option B. And you'll have to type in your 460, 0.5, 251. When you do that, and we round to our three significant figures, that gives us 0.978. Now remember, that is the probability of winning 251 or less games. If we want the probability of winning 252 or more games, we want the complement of that. So we are going to do 1 minus our 0.978, which gives us our probability of 0.0225. 4. Now, that helps us, but it's not our final answer. We want to know, is it significantly high? So we would say the probability of winning 252 games or more is 0.0224, which is less than our 0.05. So it is significantly high. Now, we've also seen that there's more than one way to word this. So we could also say it is unlikely that we would have 252 or more wins by chance. As we've seen before with that inferential rule, that means that we ruled out chance, so we're left with the more reasonable explanation that the team winning the overtime coin toss had a better chance of winning the game, right? There's probably something wrong with our assumption. Let's look at another example. Based on a Harris poll, 60% of adults believe in the devil. Assuming that we randomly select 5 adults, we want to find, in part A, the probability that exactly 3 of the 5 adults believe in the devil. So if we look at this, we're randomly selecting 5 adults. So that means that our N equals 5. Our P, our probability of success that they do believe in the devil, is that 60% or 0.6. So if we look at part A, they're asking us for exactly 3. So that means our X equals 3. Because X is only one number, we're going to use our binom PDF. If we do that, when we type it in, we're going to see that our trials are 5, our probability of success is 0.6, and our X equals 3. When you plug that in and round to our 3 significant digits, we get that our probability of getting exactly 3 of the 5 adults to believe in the devil, getting that as our responses, is 0.346. If we look at part B, it says the probability that the number of adults who believe in the devil is at least 2. So if we want at least 2, that really means 2 or more. So there's 2 different ways to approach this. If we want 2 or more, that means we can take the probability that 2 say yes, 3 say yes, 4 say yes, and 5 say yes, and add them all up. You could calculate those individually using your binom PDF, or you could put them all in a list. Remember to put them in a list. You go to L1 and fill in the numbers 0 through 5 because our N is 5. So we have those 6 possibilities that 0 people say yes, 1 person says yes, and so on up to 5. Then you would do your binom PDF. You would leave your N5 and your P.6, but leave your X blank. Then you hit the STO arrow button that's on top of your on. And then you choose L2. You get L2 by hitting second and then the number 2. When you hit enter, it puts all of those values in L2 next to their corresponding value. So when we add them up, we would have our 0.2304 plus our 0.346 plus 0.259 plus 0.078. When we add and round to our three significant figures, that gives us about 0.913 as our probability that at least 2 people said yes. The other way to approach this is to use that binomial CDF just like we did before. So our probability of at least 2 is the same thing as 1 minus our probability of 1 or less, right? Our 1 or 0. So to figure out this probability of 1 or less, I'm going to use that binomial CDF, which will give me 1 and below. So my number of trials is 5, my probability of a success is 0.6, and I want 1 and below, which gives me 0.08704. Now, for my probability of at least 2, I do 1 minus that 0.08704. That gives me 0.91296, and when I round to my three significant figures, I get the same answer that I got using the table. So either way, we're going to get the same answer. It's just a matter of what makes more sense to you. If we keep going, we see that we can also use our formulas from our formula sheet to find our mean, variance, and standard deviation. We also see the same range rule of thumb that we've seen throughout the class. So if we look at that same overtime example from our NFL, the first thing they're asking us for is our mean. From our formulas, we know our mean is N times P. 460 was the number of trials, 0.5 was the probability of success, and when we multiply, we find that 230 games is the mean. If we're trying to find the standard deviation, we know that's the square root of N times P times Q. Our N is 460. Our probability of success was 0.5, so our probability of failure must also be 0.5. When we multiply that out, we get about 10.7 games. Remember, because our games were measured in a whole number, we want to go one decimal value past it to get that 10.7. Now they're asking us to use our range rule of thumb. So we know for significantly low values, that's our mean minus 2 times our standard deviation, which is 230 minus 2 times 10.7, which ends up giving us 208.6. So 208.6 games or lower is considered significantly low. If I look for significantly high, I'm going to add my 2 standard deviations instead. When I do that, that gives me 251.4 games. So anything above or including 251.4 games is considered significantly high. So for part C, we would say yes, 252 overtime wins is significantly high because it is above our 251.4 games. And then we just have a reiteration of our probability values if we chose to use them instead. Now, if we look at our hypergeometric distribution, this is a special case of our binomial distribution. We saw before that our binomial distribution has to have independent events. So if we're using a small finite population without replacement, it will end up being dependent events, so we cannot use the binomial distribution. When that is the case, we instead use the hypergeometric distribution. If we look at this, we're going to focus on this second formula with the stars next to it. And our definitions are that A is the total number of successes, B is the total number of failures, N is still the number that we sample or our number of trials, and X is still the number of successes that we actually want the probability of. What it ends up looking like is this is the number of ways that we can get the wins that we want. This is the number of ways that we can get the losses that we want. And then this is the total number of ways that we could actually pick those things. So if we look at an example, in Pennsylvania's Match 6 lotto game, a bettor selects 6 numbers from 1 to 49 without repetition, and a winning 6-number combination is later randomly selected. Find the probabilities of the following events and express them in decimal form. Now, in the past, we've always been able to use that 5% rule for cumbersome calculations. So if we look, we're selecting 6 numbers from a population of 49. That gives us about 0.122, or about 12.2%. So our sample is larger than 5% of the population. So we cannot assume that they're independent events. That's why we have to use our hypergeometric formula. So if we look at this, remember our A was the total number of winning numbers. Okay. So if we look, there's 6 winning numbers. So our A is going to equal 6. So our B is the number of losing numbers. Well, if there's 49 total numbers and there's 6 winning numbers, that means there's 43 losing numbers. And our N was the number that we sample, or the number that we pick. So we are picking 6 numbers every time. So just like with our binomial distribution, those are going to stay the same every time. The only thing that's going to change is our X. If we look at part A, they're asking for the probability that we get exactly 4 winning numbers. So that means our X equals 4. Our hypergeometric formula was A choose X times B choose N minus X all over A plus B choose N. So our A was 6. We want to choose 4 of those 6 winning numbers. Our B was 43. So our N minus X is 6 minus 4, or 2, which makes sense. There's 43 losing numbers. We want to choose 2 of them. Our A plus B, or 6 plus 43, gives us the 49 total numbers there were. And every time we pick, we choose 6 of them. So we're dividing by the total number of ways we could choose 6 numbers. When we plug this in our calculator, it'll show us 9.69 when we round to 3 significant figures, and then it'll say E negative 4, which we know means scientific notation, times 10 to the negative 4th power. So if we write that out, we know that's a very small probability of getting exactly 4 winning numbers. Now, if we look at part B, it's almost the same exact question. The only difference is we're going to get all 6 of the winning numbers. So this time our X is going to equal 6. So we're going to stick with that same formula because we're still dealing with our hypergeometric distribution. So our A, there's still 6 winning numbers. we want to choose all 6 of them. There's still 43 losing numbers. We don't want any of them. There's still 49 total numbers, and we still have to pick 6 of them. If we multiply this out and round to 3 significant figures, we get 7.15 times 10 to the negative 8th. Remember that negative 8 tells us to move our decimal point 8 places to the left, which gives us an even smaller probability of winning the jackpot, getting all 6 winning numbers. Now, last but not least, we want to see what's the probability that we will get none of the winning numbers. So that means our x equals 0. We still have our same basic hypergeometric formula. So there's 6 winning numbers. We don't want to get any of them. There's 43 losing numbers. We can pick any 6 of them. And then there's still 49 total numbers, of which we have to choose 6. When we plug that in and round to 3 significant figures, we get a much higher probability.